So let's start with the first formula for area, the 1/2 base times height, and see how you could get to the second formula, 1/2 AB sine theta. Or maybe you started with the second formula, and that's fine as well. If you started with 1/2 base times height for your area formula, your base would be fine because we know this length is y, so that base is 5. But I don't know this height. However, I know the height makes a right angle with the base, and so that builds a right triangle. And for that right triangle, I know x is 4. So if I'm looking for what's opposite and I know what's adjacent, I'm looking for what's opposite and I know the hypotenuse, then I could use sine. And so I could say the sine of theta is opposite h over hypotenuse x, which is 4. Multiply both sides by 4 and we'll get h is equal to 4 sine theta. So if we replace h with 4 sine theta, then that would be 1/2 one side times the other side times the sine of the angle in between them. And that is exactly what this alternate formula was. Area is 1/2 one side times the other side times the sine of the angle in between them. So whichever of those formulas you use, we would all be at the same place right now. We would have 1/2 times 5 times 4 times sine theta, or 10 sine theta. So that's the formula that we're going to take the derivative of. The derivative of a would be dA dt, and the derivative of 10 sine theta would be 10 cosine theta, times the derivative of theta in terms of t. Now let's plug in what we know. dA dt is what we're trying to find, and we know that theta is pi over 3, so let's plug that in, and we know d theta dt is 0.06, so let's plug that in. So then we can go through and say 10 times the cosine at pi over 3, which is 1/2, times 0.06, and we'll get 0.3. And for our label, theta was being measured, area was being measured in meters squared, and our time was being measured in seconds. So that's the label that we want to put on our answer. All right, then the last one, number 25. Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure P and the volume V satisfy the equation PV is equal to C. So they've given me the equation that equates my quantities, where C is a constant. Now that's important because remember that when you put the constant in before you take the derivative, and when you take the derivative of a constant, it's 0. Suppose that at a certain instant the volume is 600. So, okay, volume is 600. The pressure is 150. The pressure is increasing at a rate of 20, so the rate of change of pressure is 20. At what rate is the volume decreasing? So what's the rate of change of the volume? So let's go through and take the derivative of our formula. So we could say this is a product, so we're going to do first times derivative of second plus second times derivative of first, and then the derivative of a constant would be 0. Now we're trying to solve for dV dt, so let's get that, plug in what we know. So we'll put 150 in for P, because we were given that. dV dt we don't know, we're trying to find that. Put 600 in for V, and put 20 in for dP dt. So 20 times 600 is going to give me 12,000. So 150 dV dt plus 12,000. Subtract that 12,000 to the other side and divide by the 150, and we'll get -80. And again, it's negative because it's decreasing. And our units are going to be the rate of change of the volume in terms of the time. So our volume was centimeters cubed and our time was minutes.